the following exercise, we will consider the question of finding basis of the Euclidean three-dimensional space R3. In particular, we will be posing ourselves the following questions. Find the basis of R3 without any restriction, and this is going to be quite easy and obvious. The next step, harder, is construct a basis starting from one vector in R3. So we have a condition which is starting from a fixed vector in R3, and we wonder how we can complete this vector to a basis of R3. And the third question is going to be find the basis of R3 satisfying some other conditions which might be more restrictive than the one at the point 2. Not just starting from a vector, but some more complicated conditions. So the part 3 will be covered in the next exercise. Now part 1 is obvious because we know that R3 has a canonical basis. So if we just want to find any basis for R3, we can just list the canonical basis that is formed by the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this certainly will do it. Now, if you want to see what the basis is and the definition, the main properties, you can check the lecture 5.6. Let's now consider exercise number 2. Construct a basis starting from a vector in R3. Now we fix a vector v in R3, and there are two possibilities. If v is the zero vector, then we know from general theorem of the basis that v cannot be part of any basis. So we are already halting our process because we cannot complete v to any basis in R3. So v, w2, and so on up to wk be vectors. We can always find a linear combination of these vectors, which is non-trivial, that is, not all the coefficients are 0, that give the zero vector, namely the linear combination that takes the coefficient 1 for v and then 0 for all the other vectors. This is a non-trivial combination because it has the coefficient 1 for one of these vectors, namely vector v. The linear combination is going to yield the zero vector because all these summands are 0, and the first summand is going to be 1 times v, which is 0, so it's going to be 0 as well. So that is a non-trivial linear combination of this vector that gives the zero vector, therefore they are linearly dependent. So the zero vector in any set of vectors is going to make this set a set of linearly dependent vectors. So it cannot be part of any basis. Therefore, we better start from a vector v different from 0 if we hope to eventually find the basis of R3. Let's say, for example, that v is going to be equal to the vector 2, 3, 3, which is drawn in the following way. So you see the coordinate x 2, the coordinate y is 3, and the coordinate z is 3. So we have v placed in a three-dimensional Cartesian coordinate axis system as so. Now recall that by the basis extension theorem, which we covered in the lectures 5.4 and 5.5, we can always complete the set formed by just the vector v to a basis of R3. Now we want to do, so we know we can do it, but we want to find now a procedure to actually do it explicitly for this vector v. We know that R3 has dimension 3 as a vector space, so eventually we will need 3 linearly independent vectors. Now 3 linearly independent vectors, by a corollary of the basis extension theorem, will also be generators, therefore will be a basis of R3. Now we are starting from 1, the set of v itself, and so we need to add another vector, namely u, which is going to be linearly independent with V. How do we do that? Now in lecture 5.1 and 5.2, we have shown that this amounts to pick a vector u that does not belong to the vector space generated by V. So if you want to get a vector that is linearly independent with a certain number of other vectors, we just have to pick a vector that does not belong to the subvector space generated by these other vectors. So in this case, these other vectors is just one, is V. So we just need to pick a vector that doesn't belong to the vector space generated by V. Algebraically, U must not be a multiple of V, because the set of linear combinations of just one vector V are just multiples of V. Geometrically, U must not belong to the line through 0 and the 0 vector and V. Let's check out the geometrical situation of what we have just said algebraically. So this is V, and this is a certain number of linear combinations, about 1,000 of them, of the set of vectors formed just by V, so of multiples of V. As you see, geometrically, they all lie, these linear combinations, they all lie on the line passing through V and the origin of the axis. And indeed, we can clearly see the vector space generated by V now as the straight line passing through all these linear combinations that we have just seen. So we need a vector that is not a vector u that is not a multiple of V. For instance, let's pick u equal to 3, -1, and 2. Certainly is not going to be a multiple of V, because there won't be any alpha for which alpha, a real number alpha, for which alpha times V is going to be equal to u. Therefore, u does not belong to the vector space generated by V, and V and u is a set of linearly independent vectors of R cubed. Now notice that VU cannot be a basis of R cubed, we mentioned this just a few moments ago, by a corollary of lecture 5.4, so of the basis extension theorem. All the bases of a vector space have the same number of elements, and we know that the canonical basis of R3 has 3 vectors. That means that R3 has dimension 3, therefore any basis of R3 must have 3 vectors. Now we just have 2 of them. We are searching for a third one. Before searching for the third vector, it's helpful to consider the geometrical interpretation of what we have just said. The vector u that we have chosen is, as you notice, is clearly not on the straight line passing from V and the origin. And as we said, since it is not a multiple of V, then linearly independent with V. To see this geometrically, we just take the set of linear combinations of U and V, and we will see that it's no longer one-dimensional, but it's going to be two-dimensional. So you see these are a few thousand linear combinations of U and V, and they are all vectors in R3, and they are no longer staying on the vector space generated of V, as you can clearly see, and in fact they stay on a plane, and this plane is the vector space generated by V and U. This shows geometrically that U and V are linearly independent. What is the property that our third vector must have in order at that point to make V, U, and our third vector, which we will call W, be forming a basis of R3? We need a vector W in R3 such that V, U, and W will be linearly independent. This is enough for the basis extension theorem to show that they are also generators of R3, because R3 has dimension 3. This set will be a basis because of last corollary of lecture 5.4. This is exactly where we explain the connection between basis extension theorem and what we have just said. Finding such a W will be a bit more difficult than finding the vector U, So W should be chosen so that W does not belong to the vector space generated by V and U, both of them together. Not just the vector space generated by V or the vector space generated by U is not enough. They does not have to belong to the vector space generated by both V and U. So what does this mean in practice? So of course should not be a multiple of V or not a multiple of U, but this is not sufficient because there are also linear combinations of V and U, arbitrary linear combination with coefficients alpha and beta, which are in this set, in this subvector space. So W should not be of the form alpha V plus beta U for any alpha and beta in R. So this is the algebraic condition that W has to satisfy. And what does this condition mean geometrically? Well, geometrically, the condition amounts to finding a vector W not belonging to the plane which is the subspace generated by V and U that we have just seen. Well, in practice, how do we do that? Well, we might use some fancy machinery that we will learn in the next lectures. But at this point, we may just try to guess a vector W with coordinates that are, in a sense, different enough from V and U, and then next step, check that the set of V, U, and W will be all linearly independent. This can be pretty easily done, but at this point we don't really have a specific algorithm that provides us of a W satisfying this property automatically. Let's see, for example, if we pick the vector W -2, -3, and 4, then we have learned a procedure to check whether the set of V, U, and W is a set of linearly independent vectors. Now, by definition of rank of a matrix, and we talked about this in the lecture 6.6 and 6.7, we know that the set V, U, and W will be of linearly independent vectors if and only if the rank of the matrix formed by these three vectors as columns, first column V, second column U, and third column W, will have rank 3. This is essentially one of the possible definitions of rank. Therefore, we reduce the question whether these three vectors are linearly independent to the computation of the rank of a matrix. What are the techniques that we have learned so far to compute the rank of a matrix? Well, we know how to use row elementary operations to make the matrix in a row echelon form, and then we can tell the rank of this reduced matrix just looking at it, and we know that acting with row elementary operations will not change the rank of the matrix. Let's start from the matrix V with the vectors V, U, and W as columns. So here we have 2, 3, 3 as the first column, 3, -1, 2 second column, -2, -3, and 4 the third column. So we operate with the R3 minus R2 that will be replacing the row R3. So the third row minus the second row will be put in place of the third row. We'll be getting a 0 here as the first entry of the third row. Then the next row elementary operation is going to be R2 minus 3 over 2 times R1, and this is going to be in the second row, R2. We are going to kill these 3 using these 2 of the first row, and we will be getting this new matrix. Now we have 2 zeros below the number 2 in the first row, and this is good. Now we have the last step in order to reduce to row echelon form, which involves using this coefficient here, -11 divided by 2, to kill the number 3 in the third row. So the operation is R3 plus 6 over 11 times R2, and this is going to replace the third row R3. We get this row echelon form reduced matrix with the elements along the diagonal, which are 2, negative 11 over 2, and 7. Therefore, this matrix has rank 3. So the vector that we guessed, negative 2, negative 3, and 4, actually makes the set V, U, and W a set of linearly independent vectors. Therefore, they are a basis of R3 for what we said before. Now that we have solve the questions by algebraic means, see how all this procedure is being described in geometrical terms, looking at the three-dimensional Euclidean space. This is exactly where we stopped before. We have the vector space generated by V and U, and we have to pick a vector W which lies outside this plane. So the vector that we have chosen is precisely this, with coordinates negative 2 x coordinates and negative 3 y coordinates and negative 4 z coordinates. Okay, now let's see if we take linear combination of these three vectors, what we get. So if we get vectors that lie on a plane, in which case the plane must be the plane generated by V and U, then W will be linearly dependent on V and U. Otherwise, if the linear combination will be spread around all the space and not on the specific plane, the violet plane generated by V and U, then that will show geometrically that these three vectors are linearly independent. Let's see if we take few thousand linear combinations of these three vectors, what we get. There you go. As you can see, they do not fit on all on the plane generated by V and U. That shows geometrically the linear independence of these three vectors, and that these three vectors form indeed a basis of R3.